My name is Hazim Gaber, and today we're going to start looking at fiber optic cable transmission principles. So, we've covered copper, and now we're going to think about fiber. And so, fiber is basically a long piece of glass, and we have a transmitter and a receiver. So, the idea is the same like the copper, but the only difference is we've got glass and we've got a laser beam and we've got a light pulse traveling down the strand. So there's a transmitter, which is either an LED or a laser, and then it's sending light at a wavelength of either 850, 1300, 1310, or 1550 nanometers. And we call this the central wavelength. So when you think about it, if I have a laser beam and it's generating pulses of light and I've set it to 850, it's not every pulse is gonna be exactly 850. I might have some that are like 840, and I might have some that are 860, some that are 851, etc., etc., etc. So if I were to make a chart and I said intensity and wavelength, my light would hopefully look something like this. So most of my light from a laser is gonna be very close to the central wavelength. And then this width is called the spectral width, i.e. the variance. Now, if I had an LED, I'm more likely to have a wider spectral width because LEDs are a bit lower quality. And mind you, this isn't very wide. But we can measure kind of if we looked at halfway of the intensity, what is the width? The second thing, so this 1 and this is 2. Third thing we want to look at is the power or average power, which is measured in megawatts, milliwatts, or dBm. So when you look at this fiber optic strand, we send the light down the strand at a certain power. Some of this light's gonna dissipate, especially if there's a splice here or something. And so the more loss we have on the strand, the more power we need at the transmitter to ensure that our signal makes it to the receiver. And so we have to be very careful that we adjust the power. So the fourth thing is what we call modulation frequency. So the way this system works is it's sending pulses of light. So it's like a guy on a hill with a flashlight, and he's turning his flashlight on and off, on and off, on and off. And the LED is doing the same thing. It's turning on and off, on and off, on and off. And when it's on, that's a 1. When it's off, that's a 0. Laser does the same thing. But how fast can it turn on and off? That's known as the modulation frequency. And so LEDs can't operate as fast as lasers, and they're typically the maximum data rate we can get on an LED, 622 megabits per second, and on a laser we can get 50 gigabits per second. So these days, though, they're running multimode mode with 10 gig lasers. So let's take a deeper look at the LED and why we should use an LED, because it's cheap and mostly used with multimode fiber, so short distances. And our wavelength is 800 or to 900 nanometers and 1250 to 1350. And our width, spectral width, is 30 to 60 nanometers, maybe even 150 nanometers, so it's quite wide. And frequency, 200 megahertz to 600 megahertz. That's 200 megabits per second to 600 megabits per second. And our power level of -10 to -30 dBm. And then we also have lasers, and scientists like lasers. So we have what we call short wavelength lasers. These are also cheap. Can use multimode for, say, 1 gigabit per second. And so some of the stuff we use this for is fiber channel over Ethernet, which is for storage appliances. So in a data center. And our wavelength is around 780. Narrow width So we're only off by 4 nanometers. And then frequency can be high. And power can be high. Maybe -8 dBm. We've also got vertical V cells, vertical cavity surface laser. So these are about the same as the short laser, but much more, about 850 or 1300 nanometers, and a spectral width of 1 nanometer, and up to 56 gigahertz frequency. So this translates into 50 gigabit per second transmission. And then, and again, these are also used for multimode. And then we have laser diodes. And so these are very expensive. And used in single mode. And we use 1310 or 1550 nanometers with a 1 to 6 nanometer spectral width. And obviously we can do greater than 56 gigahertz frequency. And plus 4 dBm power. And quite a high power, which will kill you. Well, it won't kill you, but if you look at it, you could go blind. So be careful with the lasers. And then, on the other side, we have a receiver. How do we read the signal? And the answer is we have to match the receiver with the transmitter. So sensitivity. So if I have a 56 gigahertz laser, then I need a 56 gigahertz receiver. If I buy a cheap receiver intended for an LED that's 600 megahertz, I won't be able to pick up my signal from a high powered laser. So I need a photo detector that can convert light into power so that we can understand it. And then our receiver has to have a sensitivity which is the minimum power level we can read. So if we've got a huge loss or we've got a very weak LED, we won't be able to pick it up. We won't be able to pick up the signal. And then we also have what we call bit error rate, which is a percent of errors we can have. So these two are connected because if our signal drops, so these are published by the manufacturer. So for example, the manufacturer might say we have 1 error per billion bits at -10 dBm. So we might say that's acceptable. Now, if our power drops to say -12 dBm, our error rate might go from 10 errors per billion bits, which is bad. And if our rate drops, say, to 14 dBm negative, we have no signal. So we get nothing. So it's like a guy flashing his flashlight at the top of the hill. If you move too far, you don't see all the flashes. If you move really far, you see nothing. We also want to make sure the signal is not too high because it can damage the receiver. Alright, so that covers the transmitter and the receiver. Now think about the fiber. What kind of fiber do we want to use? Because we have to think about what do we need the fiber for? What kind of equipment? Will we connect? So there's two things here to think about. One is the length, end to end, of the longest link. And one is the data rate. Because a short link can use multimode, whereas a long link might need single mode. And so the longer the length of the fiber, the more loss we're going to experience. And so we may already have the equipment and we may not. So once we figured out the type of fiber that we need, then we can think about the type of transmitter and receiver that we have to use to achieve specific data rate. So if we look at multimode fiber, it ranges from OM1 to OM5. So OM1 and 2 are obsolete. What else is new? And then OM1 used to use a 62.5 micro meter, and everybody else uses 50/125 micrometer diameter. So if you're using OM3, you can run 850 nanometers, OM4 850 nanometers, OM5 850, and 880, 910, and 940. And this gives us a bandwidth of 2,000 megahertz. 4,700. 4,700. So, if you look at it, OM5 gives us much more bandwidth at different wavelengths. OM4 gives us a lot of bandwidth as well, and OM3 gives us about half the bandwidth. And then we've also got single mode fiber, which has a much larger distance. And we've got OS1 and OS2, which is 1310, 1383, and 1550. Here we've got 1310 and 1550. So one of the things that we need to think about is the longer the fiber, the shorter the bandwidth. So if I say that we got 2,000 megahertz, it's not per kilometer, it's times kilometers. So if our length of our fiber is 1 kilometer, we multiply that by 1 kilometer, or 2,000 megahertz. But if we're 10 kilometers, it's 2,000 times 1 over 10 kilometers, which is 200 megahertz. So we want to be careful here and not run our fiber longer than specified. And if we're getting into the 2 kilometer range, then, or even the 1 kilometer range, we need to start using a single mode, which is more expensive, but you don't have a choice. The other thing that causes distortion is called rise time. So if we've got a laser and it's just sitting there, the time it takes to get from 10% to 90% power is called the rise time. And the rise time is affected by the bandwidth and the signal. So at a very fast speed, the rise time will cause a huge distortion in the signal, and it can be really messy. And that period of time causes a lot of loss in data, or I should say a lot of errors. So the limitation on fiber optic cable, it depends on whether we're using a single mode or a multi-mode, and then it depends on the length of the single mode or multi-mode fiber, and we can usually calculate the dispersion to determine the limitation. So on a single mode, we don't really worry about dispersion, especially a single mode fiber in a single building. We're more concerned about dispersion over a length that's like 100 kilometers. But we can calculate the dispersion, and typically these values are provided by the manufacturers. It's not really something that affects the fiber during installation. On a multi-mode system, we've got a much wider spectral width with respect to the LEDs or the lasers. So there's a width of like 10 or 100 or 50 or even 100 nanometers in width, in the spectral width, and that causes what we call chromatic dispersion. So that is a lot of our data is being broadcast at a wavelength that is not useful. It cannot be picked up by the transmitter. And so these various lights follow different paths, and they end up not showing up at the same time. So if you think about it, when they sell you a piece of multi-mode fiber, they've tested it with a really, really good laser. And then when you go to install it, you're using a cheap SFP. And so your performance is different from what the manufacturer sold you. And so you have to think about what's really going to happen when you use your cheap SFP components. And there's not much you can do, but normally the bandwidth is, as I said, it's a megahertz kilometer. So then you can divide this by the length and you get the bandwidth. So my fiber was 2000 megahertz kilometer, and I ran at 10 kilometers, then I have 200 megahertz bandwidth. So I might choose either to find a shorter distance or a better fiber. So when I got, a fiber length that's 300 or 400 feet, I probably don't care. So we need to think about chromatic dispersion and also modal, which is this thing. When we decide what kind of fiber we're going to use. Because like I said, we don't know what we don't know how the manufacturer tested the fiber, but they obviously used a much higher quality laser than we did. So, with that in mind, we can pretty much classify. We have to think about our data rate and say we want 100 gig or 10 gig or 1 gig or 150 megabits. And then we can look at 2000 meters, 550 meters, 300 meters, 100 meters. So if our distance is short, we can do a decent speed. Even, 550 meters, that's 1800 feet. That's a pretty decent gigabit Ethernet connection in a building. So that's a lot more than what most applications require. So in many cases, multimode is quite suitable. Now, when we need more than either the distance or the bandwidth in this table, we're running at 2000 meters and we need 10 gigs, for example, then we have to use Singlemode. So I mentioned this earlier. You have in your multi-mode, you have the core, and then you have the cladding. And the core size is 50 micrometers, and the cladding is 125 micrometers. In the older fibers, it was 62.5. So you'll see OM1 slash OM2 or 62.5. Sorry, OM1 62.5, 125. OM2 to OM5 are listed as 50 slash 125. Now, this is obsolete. So only use OM3, 4, or 5. And the funny thing is, multimode is more expensive. in single mode, but connectors are cheaper. And so are the SFPs. So overall, multimode is cheaper. And we're looking at distance less than 2 kilometers and 155 megabit per second to 1 gigabit per second, depending on the distance. Now, the reason we changed from 62 to 50 is because the 50 has a higher bandwidth and lower signal loss on an LED. Now, the cool thing is the 50 micrometer and the 62.5 micrometer fibers are compatible with all of the connectors because the exterior portion of the cladding is the same size, and we don't strip the cladding when we terminate the fiber. So now if we look at single mode fiber, we can do 80 kilometers and 40 gigabit per second and high bandwidth, low loss. But if we look at it, the core is 8 micrometers with 125 micrometer cladding. So a single mode, it's got a very tiny core. Typically, our attenuation or loss is 0.3 dB per kilometer. So we have to use a laser because we're trying to get a very powerful, very straight signal down the core. And the cable is much cheaper than the multimode, but the connectors and the transmitters and the receivers are much more expensive because on a very long distance we have to have very precise lasers. So, having said that, when we do an installation, we can measure the loss or attenuation And then we have to make sure that it's less than the maximum permitted. And we can calculate this as a cable plus the connector plus the splice. And so typically we got 0.3 dB per kilometer times the length. And this number might change, plus number of connectors times 0.75 dB. This might change depending on the connector, plus number of splices times 0.3 dB. And of course, this number is high. I find we can get 0.01 dB on a fusion splicer. So your results may vary. So based on that, really, if we know the maximum loss, then we can plug all these numbers in. If we know the maximum loss, number of connectors, and number of splices, we can plug all these numbers in and figure out what is the maximum length of the fiber.